Hi everybody, I wanted to go over some of the concepts that you'll need to remember or will be helpful for lab number 6, and then we'll come up again on the second test. So we'll start with snow hydrology. So if you watch the lecture that I posted, you'll remember me talking about the large wedge cutter, right? That's this large density cutter, has a little handle on the back, and the volume of this is 1,000 cc's or centimeters cubed. And the way that we use this is in a snow pit. We make continuous measurements just like this all the way down the full profile of the snow pit, and then we can use these density measurements and the depth of the pit to calculate the snow water equivalent. So let's just work through the units here. Once we take the cut, once this is filled with snow, then we place it on a scale and we get the mass of the snow in grams. So just for illustration's sakes, we'll say we took a measurement and it's 300 grams. So we know that density equals mass divided by volume. So this is 300 grams divided by 1,000 centimeters cubed. Now we know that we typically report density in kilograms per meter cubed. So let's do this conversion. So 300 grams into kilograms is 0.3, and then 1,000 centimeters cubed is 0.001 meters cubed. And then when you do the math, it conveniently works out to 300 kilograms per meter cubed. So the reason why this is convenient is because it's equivalent to those grams that we measured initially, which means that you can just look at your measured grams from your scale, and that's equivalent to your snow density. So if you want to calculate your snow water equivalent, there's two different ways you can do it. You can do it per cut. So for each one of these, you'll get a snow water equivalent. Or you can take the average density across your whole profile and then take your full snow profile depth. So if you want to do a SWE calculation per layer, you can do SWE equals the density times the depth. So in this example, right, we were doing 300 kilograms per meter cubed times the height of the density cutter, which is 10 centimeters. So if we do that in meters, now let's say we want to do it across the whole snow pit. So if we do snow water equivalent and you take the average of all of your cuts, say then that the average of all of your cuts is 300 kilograms per meter cubed times your total depth, which in this case we'll just use as an example 275 centimeters, which would be 2.75 meters. We would get 825, right, kilograms per meter cubed. Now just to sort of sanity check this rate is one layer. This is the whole snow pit. If you were to add all of these up across the whole snow pit, you would end up with this same value. But these units don't necessarily correspond with the way that we think about snow water equivalent, which is the amount of water that would result if we were to melt it down. So if we're thinking about meters of snow, how many meters or centimeters of water would result? And in order to move from the kilograms per meter squared to units that would be, say, just depth to depth, then we have to account for the density of water. So that is the equation that I have up here. So this then actually returns the amount or depth of water released from a snowpack if entirely melted. So the way that this equation then ends up looking like is the density of the snow over the density of water. Right, so units cancel. We're left with a depth here, and the answer is 0.825 meters, which is equivalent to 82.5 centimeters. And then if we were to then go back and to find out the percent of water, we would have to account for the depth, and this would be 30% water content for this snowpack. Okay, so another thing that I mentioned in my lecture was the snow sampling tube, which is otherwise called a federal sampler, right? This was originally called a Mount Rose sampler, and it was developed by Dr. Church. Sorry, that's supposed to be a tube. Has a little cutter on the end. You insert it into the snow, right? So here's your snow layer, here's your ground, and then you end up with a snow core within that tube. And then you pull the tube back up, you place it on a scale that actually looks something like this, right? So it has these little hooks that hold the scale, and then you record that measurement. And snow hydrologists really like to make it easy on themselves. So in the not so recent past, the tube diameter of the federal sampler was actually standardized to 1.485 inches. And if you work it out, 1 inch of snow then within the tube is exactly equivalent to 1 ounce of weight. And what it allowed them to do is to make scales that actually report not the mass of snow within the tube, but the snow water equivalent directly by taking this into account. So these are actually typically used on snow courses, and snow courses happen in the same spot multiple times a year and throughout the year, so that we get a consistent record of snow water equivalent. And what a snow course means is just that multiple measurements are taken at known sampling distances, and then you take the average of all of those measurements to get SWE of your study plot area. Most of these snow course sites were actually selected where there is little wind effect, so typically below tree line, where there's relatively stable snowpacks that last for a while, so north-facing slopes. This made it easier to correlate snow water equivalent to stream flow, and this also means that these sites tend to hold snow for the longest, and this really biases this data collection towards higher SWE values than is actually held up in the mountains. Okay, so that covers how to look at snow water equivalent at a single discrete point. But what if we want the snow water equivalent over an entire watershed? In order to get volume of snow water equivalent, then we need a couple different things, right? So we need the area, the depth, and the density. And remember, depth times density equals SWE. So if we have area, this could be in meters cubed or, meter squared, kilometers squared, some sort of measure of area. And then SWE, remember, that can be in centimeters or meters, etc. So to keep things simple, if we do meters squared times meter, then we get the volume in meters cubed. if only it could be this simple, but typically, if you think about a large watershed, maybe here's the pour point. Sorry, these are some weird mountains. But, all the water here is eventually, if it's held as snow, is eventually going to melt and then run off to this point, what we call pour point. And we might only be measuring snow water equivalent at a few points in this basin. So it's not quite as easily as just interpolating between these points. You might have to account for elevation, variations in snow depth, variations in where snow actually falls and how that impacts snow depth and snow density. So there's a lot of relationships that have been developed over time in order to get a basin-wide estimate of snow water equivalent. There's also technological advances like LiDAR and mapping from airplanes and drones that have allowed us to measure snow depth over an entire basin. We can then take those snow depths over the basins, time them times a modeled or assumed snow density to get to snow water equivalent, and then you can just integrate over the whole basin. Okay, so moving on from snow water equivalent towards snow energy balance and calculating melt from your energy balance contribution. So if you remember correctly from the energy balance equation, this Q sub M term is the sum of all energy balance terms. And when it's positive, that means, or when it's positive and all of the snow is at 0 degrees C, that means energy is going to melt. So this is actually a relatively straightforward calculation if we actually know Q sub M, because we know how much energy it takes to turn ice to water. And that is 334 kilojoules per kilogram. So this value, the enthalpy of fusion of water, let's just go back to when we talked about thermodynamics. Remember that the liquid phase of water has higher internal energy than the solid phase, which is an ordered matrix. And this means that the energy has to be supplied to the solid in order to melt it. And then energy is released from a liquid when it freezes. So we know that we have to add this much to go from solid to liquid. But this unit in kilojoules per kilogram is not directly comparable to what we report in energy balance, which is in watts per meter squared. But what we do know, right, is watts equals joules per second. So now we have joules here, and we have joules here, right? So 334 kilojoules per kilogram, or 334 joules per gram. And we can connect these using joules. But what about the seconds? We integrate over some time frame, and what this becomes is that we can get watts equals joules over seconds, which means joules equals watts times seconds. Okay, so let's fill in some numbers here. Say that over an hour, we have 400 watts per meter squared net solar radiation. In 1 hour, we have 3,600 seconds. So if we want to go from 400 watts per meter squared over an hour, we would have to take 400 watts times 3,600 seconds to get joules. And this gives us many joules and 1,440 kilojoules. If we divide this by the enthalpy of fusion of water, which is 334 kilojoules per kilogram, what we end up with is a value with the units kilograms per meter squared, remember? This was in the original equation. So this 4.31 kilograms per meter squared is the amount of melt that is produced from this amount of net solar radiation acting on the snow. So this is actually equivalent to millimeters of SWE. So that's just over 1 hour, but you can do this over any time interval you want as long as you know the net solar radiation over that time interval. You can also work backwards, and if you have a total amount of SWE, say that you have 450 millimeters of SWE, and you know that you're melting, approximately 4 millimeters every hour, you can calculate how long it would take to deplete that snowpack. There are a couple things you really need to keep in mind here, though, and one of them is that the sun only shines for a certain time frame during the day. You can't calculate this over a full 24 hours. So you need to know when the sun rises and the sun sets, and you also know that the intensity of solar radiation, right, has a bell curve throughout the day, being highest at solar noon, when it's at peak solar zenith angle, or the highest point in the sky. So if you're going to calculate this over a day, you have to know the net solar radiation and how that varies over the course of the day to calculate daily melt. So that's all I have for you on calculating melt from snow energy balance and net radiation, or the sum of the energy balance terms. Hopefully this helps on Lab 6 and test number 2.